Our next speaker is then Hamish Todd from Traceoid of the UK with the title Visualizing de Sitter and Conformal Spacetime Transformations with Curved Reflections.
Brilliant. Brilliant. Thank you so much, Avril, and thank you so much to Parvo for organising this and for inviting me. Right, let's get into it. I'm going to say a little bit of biology first. So this is, in some sense, your great-great-great-great-great-great-grandmother, all right? This is a creature that was one of the first creatures to have something like eyes. And this creature is much slower than the speed of light. And it's much smaller than the radius of the universe. And consequently, it evolved a brain that uses Galilean relativity, so no time dilation, no space dilation, and it has Euclidean distance. It doesn't expect the universe, it doesn't take into account curvature of space. But, you know, we're developing as a civilization, right? We want to move beyond this. And you might say, well, you know, I've developed my brain, my brain is evolved to do distances in this way. It's just really hard to try to learn to think about space and time the correct way. And some people say, oh, can't I just stay with the algebra? Can't I just do algebra? No, you need to do some geometry sometimes. You need to think about the shapes of things. I mean, sometimes you get very complicated diagrams like what we're going to be showing, but let me show you some quotes to kind of motivate this. So here's Albert Einstein, and here's a quote from Albert Einstein. The words or language as they are written or spoken do not seem to play any role in my mechanism of thought. Sorry, I should have said, so this was in a letter to his friend Jacques Hadamard, and he says, the physical entities which serve as elements in my thought are certain signs or more or less clear images that I can combine, and the above mentioned elements are, in my case, of a visual and of a muscular type. That's quite amazing, right? From Albert Einstein. And it's not just Albert Einstein. Here we have Paul Dirac, and Paul Dirac once said, there are essentially two different ways of thinking about mathematics, the algebraic way and the geometric way. A good mathematician has to be master of both, but my own preference is especially for the geometrical way. That's amazing, because Paul Dirac didn't have a single picture in any of his publications or his books. I mean, a single picture. Maybe there was one or two here and there. But for a guy saying that he primarily thinks about images, that's incredible. And when, so Robert Oppenheimer, when he was told that Dirac thinks in images, he says, that can't be true, that can't be true. Because Dirac was very, very, well, he was difficult to talk to. And he didn't really tell us what exactly was in his mind. He also said, well, I'm no good at doing massive algebraic calculations without picturing what the equations mean. One more quote here. This is from Yvette Fuentes. I feel the physics in my body. We heard her say it about an hour ago. If you want to be like these people, draw pictures and think about pictures. For goodness sake, I'm not saying stop doing algebra. Do algebra and pictures. That's your job, not just algebra. Goodness me. All right. One more. Leonard Susskind. This is Leonard Susskind, Stanford theoretical physicist, major string theory, major quantum chromodynamics guy. He said in this lecture he was giving about cosmology, studying that picture will tell you more about cosmology than any of these equations. A little bit sad, because he then went on to do lots and lots and lots more equations, not so many pictures. One or two pictures, fortunately, more than Dirac. But anyway, the picture that he's talking about here is stereographic projection, and I'll be getting to that in this talk. One final note, so spherical and de Sitter universes. Well, Tuomo Santola here is obviously dynamic universe is a spherical universe. But it's not just Tuomo Santola that believes that the universe is spherical, I want to point out. So this is an aspect of the, what's it called, the cosmological constant. And this has been measured by this Hubble Space Telescope. And if this number was exactly 1, then the universe would not be spherical. The universe would be flat. But, as you see, there are some error bars here. So there's still room to, certainly there's room to believe that the universe is spherical. And actually, you know, Okay, it seems like a really, really close to one, but actually it just would tell you that the universe is a very large sphere. All right, so it's not just Tuomo. My colleague Anthony Lazenby has also he's been working on all his life on radio telescopes, and he's created. He's also a fan of the idea of a spherical universe, not in the same way as Tuomo, not with dynamic universe. He has a completely mainstream view of special relativity. Yes, so he's also got a prediction that he made in a paper that I put here. All right, so to tell you what I'm actually going to go through in this talk. First of all, we're going to think about rotation and translation invariants and their algebra, starting from reflections. If you want to think about space-time geometrically, you must think about the valid transformations. And by valid, I mean distance preserving. And building those out of reflections is a very powerful way of doing that. It's also the Clifford Algebra way. So then as I say, I'll get to stereographic projection, which is a very good way of making it so your flatworm brain can think using the neurons that you've evolved about a spherical space, it not feeling too unflat. Okay, then we'll get to space-time, not just space, and then we'll talk about something called polarities if we get to it. All right, so part one, rotation and translation invariants and their algebra. So here's what I mean by a transform invariant, and if you're a physicist, then transform invariants, I put to you, are very, very important things. So quantum measurement operators are often defined using Lie algebras, and Lie algebras are essentially transform invariants. If you want to think about Noether currents, or certainly de Sitter transformations, so transformations of a spherical universe, it's very, very helpful to think about these things. Now, on the right here, I've got a vector field, and I put to you that thinking about the invariants of the vector field is better than looking at the vector field itself. Sorry, I say thinking. Visualizing. If you had decided that you were going to visualize this vector field, here's a better thing to do. You can look at that. All right? There's the vector field. Those are the invariants of the vector field. There's a particular preserved axis, and there is also this line at infinity. I'll get to that in a second. I want to say, so there's some examples from everyday life of thinking about transformations in terms of invariants. So getting a little bit biblical for a second, the three wise men were told, follow that star, and they go towards the star. They don't turn. That means the star stays where it is from their point of view. They keep moving towards it. Here's a screw that we've got down here, and this screw, if you're ever reading instructions on it, you've got to turn it around a certain axis, and you want to move forward in a certain way as well. You're actually preserving what we call the screw thread here. That's an invariant of the transformation. And here's Leonard Susskind again, talking about cosmology, and he's using his hands in this part to gesture and say, in an anti-de Sitter universe, he happens to be talking about there, in an anti-de Sitter universe, you would be pushing away from a certain point and towards some other point. And then he doesn't talk about the algebra of those invariants, but I'm going to talk about the algebra of those invariants, because I love Clifford Algebra. And I've made a little simulation here based on Clifford Algebra. Just compile it. We'll get there in the end. Okay, so we just want to think about two-dimensional space. Here is a line, and a line can do a reflection, all right? I can move this fish around, and we've got a reflection of our fish. I'm going to move this around, and that changes where the fish is reflected to. I can also rotate it a little bit, and the reflection does what you would expect the reflection to do. And I'm going to leave this here, and I'm going to make another reflection. And we also see that thing reflected there. And you can say, what would happen if, and this is something that Basil Hiley was very interested in doing, what would happen if I did a reflection in this line and then a reflection in that line? And the answer is I would get a rotation. I get a rotation of my fish. That's the rotation that it is doing. If I move this line around, you can see that the axis of the rotation is changing where it is. And if I make the, let's say I make the rotation, I make the reflections closer and closer to each other, and eventually it's basically like you're not rotating at all. And if I have it all the way like this, then it's a huge rotation, because you're reflecting in here and then you're reflecting in this line that's a large angle away. Now here's a rather mind-blowing thing, at least I think that this is mind-blowing. So we're going to take a slight change of perspective now. We're looking at the same thing, but now we've got the horizon line up here, all right? The horizon line, you're all familiar with this. I'm going to move this line around, and I'm going to slowly change its angle. And I want you to notice, sort of notice what happens to this point, but also notice what happens to these arrows, all right? As I hold it in place and I move it towards being eventually parallel with that line, suddenly we've got a translation instead of a rotation. Because a translation is a rotation. It's just a rotation around an axis that's at infinity. See, there's that point there. Here's our two lines. If you were to continue them all the way up, you would get to that point. They meet at infinity. That's sort of the definition of being parallel. And any time that you have reflections in two parallel lines, you have a translation. And if they're not parallel, then you don't have a translation. Now, I really, really love that. I love that so much that I had that tattooed on my arm for the rest of my life. And I'm very proud of this. This particular algebra for talking about the things that I just said to you. This algebra was discovered by this guy. This is John Selig. And he's making a face because this is a picture of me showing him the tattoo that I've gotten of his own work. I think this is possibly the only picture in the world of a mathematician seeing their work tattooed on somebody. Yes, I'm quite proud of that. And you can see that I'm using some particular algebraic objects here. Oh, sorry. Some particular algebraic objects. These have been known about for quite a long time, actually, since about the 1870s. But it's only recently, partly because of their use in computer graphics, which I worked in for about a decade, it's only because of that that we've started to understand how powerful Clifford algebras are for dealing with geometry in an intuitive way, using invariants, all right? To say what I mean by that, this little algebraic object, this element of a Clifford algebra, oh, and by the way, these are things that Basil Hiley wrote a big paper on along with David Bohm in 1984, and that Callum is going to be talking about in the next lecture. Oh dear, I do beg your pardon. Not that lecture, not that particular paper, but Clifford algebras in general. No Clifford algebras. Okay, Petrie at least was talking about Clifford algebras. I do apologise for that, Callum. Okay, so planes do planar reflections, and E1, that's a plane, or rather it's a simple reflection. E12, that's a rotation, because you can make it out of two reflections, all right? It's got two downstairs indices. You could make it out of two planar reflections. It's a rotation. If you go up to 3, this has 3 downstairs indices. That's something called a point reflection, okay? And these get very sophisticated, as we'll see, but you can just have this picture in mind. Oh, and like I say, Bowman Hiley, 1984 paper, and the word process, I want to talk to some real specialists about this, but at least certainly in that paper, in some sense, these transformations are the processes. They've identified yeah, Callum is nodding, thank goodness. They've identified this algebraic object with this philosophical concept. Okay, I'm going to give you a little bit of work to do now. Okay, I believe in you, all right? I'm establishing this as an axiom. E1 multiplied by itself is 1. That's because if you take a reflection and you do it twice, what do you get? The identity. It's as if you have done nothing. If you do the same reflection twice, you have done nothing. We also define this object, E12. It's this followed by this, all right? What's this now? High school algebra to the rescue. I believe in you. You can do this. 1 plus E1, E2. E1 plus, say it again, please.
1 plus E1,
Incredible. He even skipped the step that I was going to say. So we just use distributivity, and then we just use this rule, and there it is. There's a visual depiction of this thing. That line there, that is E1. That line there, that is E1 plus E2, because it is halfway in between E1 and E2. Addition gives you the thing that's halfway in between. Basil Hiley used to call that the principle of superposition. And then multiplying them is he called the principle of succession, but I don't tend to use that technology. That point there is E12, and the rotation is 1 plus E12, because the rotation is a bit like a 180-degree rotation, and it's a little bit like the identity. It's sort of halfway in between them. The identity is 1, E12 is 180, you get it. Okay. Here's a much more advanced version of it. I'm not going to go into this, but if you're interested in this stuff, please do talk to me about it. This is what Hiley and Bohm had in their paper. And just to be clear, this is a Clifford algebra. You can represent all of it using matrices. You can. You would go mad. Really, I mean, so this is a Pauli matrix, and, I don't want to write, remember that, it's negative I in the top right and blah, blah, blah. I just want to use E1. Thank you very much. That was a little bit horrible to look at. Now let's look at a Disney movie. Frozen. Who is this? Who is this up here?
Elsa.
Thank you, Elsa. Goodness me, that took way too long. Frozen was a big moment for Clifford algebras because Disney solved a very particular animation problem using Clifford algebras. Here are some early 3D animated movies. And one thing that you can notice about all of these movies is that all of the characters have very simple joints. They have very simple joints. And that's because animating joints is rather difficult. It's not the most difficult thing in the world, but if you're having to do it all the time, it takes up a huge amount of your budget. That's because you get this problem. This is called the candy wrapper effect, because it's like you've taken that candy and you've gone like that. And that happens if you use matrices. You don't want to use matrices. You want to use the thing tattooed on my arm. You want to use a Clifford algebra. That lets you solve this problem. Okay, and this was the proudest moment of my career so far. 3 Blue 1 Brown actually quoted me on this subject. Anyway, last request before we move on from this part. We've got physicists in the room. You teach undergraduates. Right now, all mainstream courses don't teach Clifford algebra, unless maybe you get to graduate school and it's time to learn quantum field theory and people say, oh, it's all very complicated. It is not very complicated. It's not very complicated at all. It is in most ways much simpler than matrices. And, if you're good, you have to teach a version of it anyway. You have to teach the special unitary group for, Pauli. Well, you have to teach the Pauli matrices. And you could just you could give them, take 5 minutes out of your lecture to say this, and you will make it so that all of your students can get jobs as animation programmers like that. All right. Okay, part 2. I'm going to talk about stereographic projection now. How am I doing for time, Parvo?
You have still, let me see.
It's okay. Okay. Stereographic projection for intuiting spherical space. So far I've only been talking about Euclidean space, because animation happens in Euclidean space, human intuition is about Euclidean space. We're going to think about spherical space. So, again, we are evolved to think that space, and even space-time, is flat. So we really are evolved to think, basically there's just a square grid and you're going around like that. Even if you are in a situation like this one, all right? In this situation, really, this is stereographic projection, and it's a way of going from a sphere to the plane. Let's just watch this nice video from Henry Segerman.
Which illustrates stereographic projection, which is a way to map from the sphere to the plane. Maps of the world do this in a bunch of different ways. Stereographic projection is one of the simplest. Draw a line from the north pole of the sphere down inside the sphere. It hits the sphere in a point, and it continues on to hit the plane in a point. And that's the map. You send this point to this point. Here, the light rays do that map. Stereographic projection has lots of nice properties. For example, anytime you see a right angle on the sphere, you also get a right angle on the plane. It also takes circles to circles. All of the circles on this sphere map to circles on the plane.
Petri wonderfully got me my own version of this. I can actually do it now, so we'll see how it works. You can come up here and play with it after if you'd like to. I'm not so good at it yet. Maybe one day, but you get the picture. It's got a square grid on it. Okay, so used to be that stereographic projection was for cartography. I mean, this is two stereographic projections. They've separately stereographically projected the hemispheres. Really, this is proper stereographic projection of the Earth, but this is a horrible map because it's infinitely large to give you the surface of the whole Earth, and it's good in many ways. But well, anyway, that's its role in cartography. Okay, so let's compare these two situations. And the thing is that as a civilization, we still aren't sure which of these two situations we are in. Again, the number is 1.0002 plus or minus 0.0026 or something. Yeah, it could go either way. But to think about it geometrically, with these guys, their grid is naturally flat. Like, it doesn't help them to believe in any such sphere, okay? They could measure the flatness of their world and find something like that and be like, okay, we have no use for stereographic projection. With these folks, they can see that their grid is not naturally flat just by examining the circles down here. But the thing is that they still might be evolved to think about, to think as though the world is, as though the universe is flat. They're really up here, right? They're really on this sphere, but they've got. It's really. This is a really useful picture. This is why Leonard Susskind said you can learn so much about cosmology from looking at this picture, because you. The first step in getting rid of a bias is to admit that you have the bias, and we are biased towards believing that the world is flat because it's such a good approximation. That it's our flatworm brain again. All right, we want to get past that. Okay, now it's time for another demo, and I'm going to first clarify. So this is what you're going to see, and you're to imagine that the northern hemisphere is in the center of this circle, and the southern hemisphere is everything outside it. Okay, so let's go back here, and yep, and let's just do that. So I can have a reflection again. Pretty simple, right? You can have a reflection on a sphere, and this reflection actually looks like an ordinary reflection. The thing is that if I move this line away from the origin, ooh, we've got a circle, or it looks like a circle anyway. It's actually this circle is in some sense really a line, or rather, it's the closest thing that you can get to a line on the sphere, because it's being stereographically projected. It's a great circle. It's like a flight path for a plane. It's being stereographically projected to this circle. And we can still, at the same time, ask, hey, what would a reflection in that circle look like? And it looks like this. This is a completely valid thing to do. All right, this is a valid thing to do. This is a distance-preserving transformation. It looks as though we're distorting the fish. We are not distorting it. It's the same size on the sphere. It just looks a little bit like it's a different size. But again, you're evolved to look at it in this kind of flat way, so you need to get used to this. Okay, let's have another reflection, and let's compose those two reflections. We get something that looks like a rotation, but if I start moving this around, okay, it's doing the same sorts of thing that we saw with the sphere. If we look at the invariants of this transformation, oh gosh, they're a bit weird. Do not give up. This is difficult, but you're going to learn it anyway, because the universe may well be like this. Okay, you've got these two, if I put it like this, we've got a reflection in this circle, followed by a reflection in this circle, and that gives you a rotation, I mean, this doesn't look like a rotation. I mean, okay, it's got some circles in it, but it's kind of a rotation around these 2 points, you see? You've got a point here and a point here. And an ordinary rotation is around an ordinary rotation in two-dimensional space is around a point, okay? But we're being mature, all right? We're saying, hey, do you know what? Maybe we have to bear in mind that the universe is more like this, and that means that we're going to have to get used to the idea that a rotation might be more like something around 2 points. Okay. There I was making use of something called circle inversions. You might have heard about these. They are a generalization of reflections, and they're a very simple formula. If you have got a circle at the origin and it's a unit circle, then you just send the vector to the vector 1 divided by the vector's length multiplied by the vector. Very simple formula. Okay. Part 3. Now we're going to think about space-time. So everything I just said was just space. It was weird space, it was flat space, and then it was spherical space. But we're now going to think about space-time, and that is weirder. Okay, but we can also make up space-time from reflections. Reflections remain very powerful algebra for thinking about this. Here's who knows who this is? Oh, I was going to say not you, Mike. Of course you know who it is, but indeed, it's Hermann Minkowski. Okay, and Hermann Minkowski said, in, I suppose, 1908 or something, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will be preserved in an independent reality. Very deep and interesting thing to say, and if I had been around at the time, I would have said, yes, you are completely right. But he was, in some sense, wrong for 2 reasons. Number one, relativistic quantum mechanics is very difficult. That's why an initial course on quantum mechanics won't be relativistic. We will say Galilean transformations. We won't have proper boosts. We'll say that, oh, you can separate space and time, and there's an absolute preferred frame, this kind of thing. No, that doesn't obtain in real life, and eventually, at some point in your physics course, you learn relativistic quantum mechanics. But it's so much harder that we really might as well continue teaching non-relativistic quantum mechanics. And also, this guy, Willem de Sitter, another guy that Tuomo would get on very well with, he believed that, he was like, we should really explore the idea of a non-flat space. And if space is going to be non-flat, then it makes space-time, doing this part even more difficult. Okay, something to say about space-time. Here's a thing that would be very strange to see in space-time. So here we've got an ordinary graph. This is time, and this is, let's say it's inflation or something like that. We're measuring inflation over time. If you opened up the newspaper and saw a graph of inflation over time, you wouldn't be very surprised, but you would be very, very surprised if you saw this. That would be very, very surprising indeed to see in a graph of inflation over time. Why? Why would that be a very surprising thing to see? There's a few different ways we can answer that question, but my preferred way of answering it is to say that circles are just not very natural objects in space-time. And rotations as well. You can't do ordinary rotations in space-time. Why can't you do ordinary rotations in space-time? Well, if you could, then you could sort of time travel. That's sort of what that graph seemed to be saying. Somehow inflation had gone back in time? No. Okay, we can think about it in science fiction, but the universe decided to say no. No traveling back in time. Why did the universe decide to say that? Well, I mean, we could go to the grandfather paradox or something like that, but you can think of good reasons why you wouldn't, if you were designing a universe, you wouldn't want to have time travel. So, the universe decided we're not going to have rotations, we're going to have something else, okay? This is a much more ordinary thing to see, and this is a particular shape. What's this shape? I'm sure Petri knows. Very good, it's a hyperbola. Hyperbolas are to space-time, or at least 1 plus 1 two-dimensional space-time, what circles are to ordinary space. also got these things called boosts, and fortunately I've got a little, let's have her version of it, a second. Nice sounds, right? So, this is a transformation that you can perform with one of these things. If I hold this, the very center of it fixed, and I started out here, then doing this, it's actually the case that all of these grid points are moving along hyperbolas, all right? So this is the closest that you get to a rotation in space-time. You can't rotate time fully into space, but you can kind of mix them up a little bit in the same sort of, I mean, what is a rotation? Rotation is mixing up forwards with left, all right? That's one way of saying what a rotation is. If you had a rotation in space-time, that would be mixing up time and space. Well, we don't want to do that because time travel is bad. But this allows you to have some kind of mixing. That's what I would say a boost is. And once again, the flatworm brain is saying, no, 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 this is confusing. I want everything to be just rotations. Why can't I be rotating things all the time? No, no, you're going to rise above that. Rotating things is, this is just this. You're doing this all the time. When you move, when you pick up a fork, when you pick up a knife, you just don't. It's just an effect that you can't quite see. But we are moving beyond the flatworm brain as a civilization. Okay, and finally we got. We're going to have a space-time demo, and I'm going to have time going up, which is what you usually have. Okay, let's move on to this thing. Okay, not that though. So we've got a reflection. Surprise, surprise. You're getting bored of this now. And I can skew. Ooh, what's going on? I can move my reflection, but can I? Okay, good. Let's get that restarted. So I'm going to. I can move my reflection around. This is moving in space because up is time. I'm now going to skew it. I can do that. All right. Now, please notice. I've drawn some little spikes on the line to tell you what direction it's facing in. Here's an, oh, that's not really supposed to look like that. So let's get rid of that. But anyway, I've got these little spikes on the line to show you what direction it's facing in. I'm now going to skew it, all right, using this kind of transformation. What do we think is going to happen to these little spikes? Oh, we've got a very, very clever person here, clearly. He's exactly right. So it's bizarre what the universe decides to do, but here we go. If you've got a plane in ordinary space, it's facing in this direction. But with this plane, as we tilt it, the direction that it's facing in seems to tilt towards, well, it's changing in this way. And what do you want me to say? Yeah, for real. Now, let's have another one. I'm just going to show you that we can do a, as usual, we can do a time rotation. There we go. Okay, sorry. No, that's not a time rotation. That's an ordinary translation. That's a spatial translation. It's actually unphysical, but it's like a change of reference frame to being over there at the same moment. If I tilt this, oh, we can see that just as a translation in 2D space was a special case of a rotation, it turns out that a translation in space-time is a special case of a boost. Oh, I think that's interesting. Let's have one of these. I'm sorry that it looks a bit weird, but we can have two of them, yeah, because it thinks it's going for more dimensions. But anyway, you can have a... No, let's not have that. Okay. Let's go straight to... this is now 2 + 1 dimensions, all right? 2 dimensions of space and 1 dimension of time. So time is still going upwards, but we're going to think about translations, all right? And we're going to think about rotations, and there's our rotation. But we want to think about boosts as well. We're going to have that up there and this down here, and let's have that there, and let's do that, and then let's have another one. Oh, damn it. Oh, make a new one, tilt it a little bit, make a new one, compose them, and there we go. There's our boost in 2 + 1 dimensions. And if I tilt, can I tilt that? No, I can't tilt it. Let's get rid of those and think about that. I'm just going to show you the easier version to look at. So there's a rotation without any reflection planes, but I did actually make it that way. There's a boost without any reflection planes. You can see we've got these hyperbola type kind of trajectories. This is called a null rotation. I don't see people talk about this very much, but if that's a boost, if that's a rotation around a vertical line, that's something like a rotation around a horizontal line. Well, what about the thing in between? And it turns out that there is a transformation. You can read about this on Wikipedia. That's a null rotation, and the rotation has circles. The boost has hyperbolas. The null rotation has parabolas, because a parabola is somehow between a circle and a hyperbola. All right. Oh, and you can have space-time screws as well. How about these? Yeah. So you can rotate and you can translate upwards. This is translating in time while rotating, and that's the thing that I had at the beginning. And I guess that's it for those guys. Oh, this is a boost and translation. And this is a boosted screw motion. You can see there's this weird crossing effect. Similar with here. So this is a boost and translation. Okay. And now we're going to go to... How much time have I got, Parvo?
4 minutes.
4 minutes. Okay, I think that's all right. Okay, so space-time, instead of circles and spheres, instead of circles, so you could think there was a rotation and these points are all equidistant from this point. That's ordinary space. Here's a hyperbola, and all of these points are equal space-time distance from this point at the center. So they're actually defined in the same sort of way, but with a different metric. All right. Generalization of that is a sphere. Generalization of this is a hyperboloid. And my wedding ring is also a hyperboloid. I can do a fun magic trick, but you've got to be up very close, so ask me about that if you're interested to see it. Okay, polarities. I was wondering if we were going to get to this, but we can, evidently. So what's a polarity? A polarity is a thing from geometry that I think might be pretty useful in physics. So we're going to think about the polarity of an ordinary sphere first. So here's a person, and this person can move in some direction, all right? This person, starting from the North Pole, they can move in a direction. When they do this, they are actually rotating. They're rotating around this point here. And some of you who saw my presentation in London will remember how we were thinking about how a rotation in a spherical universe would be a translation around a huge circle. Anyway, he would be rotating around there if he were to walk in that direction. If he were to walk in this direction, he'd be rotating around here. All right? Is that clear? I hope that's clear. All right. Oh, I mean, just, he's confined to the sphere, right? So, yeah, so it's a rotation. Now, in fact, if he were to go in any direction, any of these directions, he would always be rotating around some point on the equator, all right? And that's his polarity. That's his position, and that's his position's polarity. I've got another toy for this, but let's skip that. Let me know if you want to see it. In Euclidean space, polarities work rather boringly. Everyone's polarity is the same. It's just the horizon line. Let's skip the quiz. Turns out that the polarity of Helsinki is the flight path from Colombia to Nicaragua. It took me a while to figure that one out. And we can skip that. And I guess we can go to the boundaries are kind of important. Let's just go back to this thing, and I'll show you. So this is a translation in 2 + 1 dimensions, all right? There's a translation in 2 + 1 dimensions with a spherical universe, it turns out. This is the generalization of rotating around 2 points to space-time. This is a null rotation in a spherical universe. It looks absolutely bizarre and fascinating, but interesting, I would say. Here's a better to show this one first. This is a just a simple translation forwards in time in a spherical universe. It doesn't look that simple, but I mean, that's actually a really simple transformation as we go, and that's a boosted translation. And this is a screw motion, so you're rotating while translating through time in a spherical universe. Don't have time for this. Apologies, Iveta. It was going to be the link to quantum mechanics, but okay, what have we learned? Invariants are really cool. Learn their algebra. It's called Clifford Algebra, for goodness sake. Translations are rotations around lines at infinity. Time translations are boosts around lines at infinity. Spherical spaces are challenging, but stereographic projection and polarities help. You are better than a flatworm. Thank you very much.
Quick questions, please.
So in the 2+1 space, the spheres you were talking
The
about...
2+1 flat or the 2+1 spherical?
Spherical.
Mm-hmm.
So that was a two-sphere then?
Yes, correct.
Okay.
Yes. Yeah. I left my four-dimensional space-time at home, sorry. Yeah. I have been working on a thing that your only choice, if you want to do 4 dimensions, is slicing. Slicing is a perfect, yeah, as in taking a time slice or a space slice. Yeah. And that is interesting. A lot more work.
Hi, thank you. I was wondering whether this interesting concept that time translations are boosted around lines at infinity could be used to make some holography, space-time holography, in an interesting manner.
I don't know very much about holography, but I do know one little thing, which is that the algebra that I've shown, so ADS-CFT is, it turns out that to say ADS-CFT in Clifford Algebra language, the Clifford Algebra of conformal space-time for our universe is equal to the Clifford Algebra of anti-de Sitter space-time for a universe with an extra spatial dimension. And that makes itself known in the algebra, absolutely. And let's talk about it afterwards, yeah, because there is a connection there, absolutely.
It could be, I mean, if it works,
yeah, it would be
really cool.
Yeah. Oh, and sorry, and Roger Penrose also, there's a lot of investigation of conformal infinity, and conformal infinity has a treatment in all of this, and conformal infinity is where the boost axis is. Yeah.
Okay.
Yes.
Okay, let's thank Hamish. Quite wonderful.